the mic. There. Perfect. Sure. So, hi everyone. So it's really a pleasure to be here today, and let me start by thanking all the organizers for this amazing event. It's really a pleasure. So I'm Léo Peyruchat, a postdoc in the group of Pasquale, and today I will be presenting our efforts to build a platform for analog quantum simulation with superconducting circuits. And this is based really on these high impedance cavities. Yeah, so before starting on this topic, I just wanted to briefly highlight another interest I have in this group, which is on the topic of strongly driven K-resonators. And for that, we have this really neat building block, which are Josephson junction arrays. And the really cool part is that we have a large control over the K nonlinearity. We have an easy way to go from the qubit regime, the transient regime, for example, where U is much bigger than kappa, to a more classical regime dominated by dissipation, where this looks more like the usual Duffy oscillator. And now I'm looking at the interplay of this nonlinear physics with this transition. And in this work here, we studied the effect of a frequency modulation of a single K resonator, where the frequency of this modulation is much weaker than the bare resonance of the resonator. And this will create a bunch of sidebands of OK states, and in some contexts known as Landau-Zinner interferences. Right? And all these sidebands are splitted by the frequency of the modulation. And now we basically applied this technique to K resonator and drive them strongly. And this is just a highlight of what we observed. And typically now all of these sidebands are themselves nonlinear, so they inherit the properties of the K resonators. And now we have a bunch of sidebands that can look like Duffing resonances in the blue case in the more classical regime. And on the right, we have also some multi-photon resonances mixing with the sidebands. And yeah, this is described in this work. I'll be happy to discuss it later. Now, for the part on analog quantum simulation, this work is actually mainly carried by Vincent Joigny, a PhD in the group. We'll be finishing soon. And we have several collaborations on different topics in this direction. Right, so one thing we really need for this is to engineer the bar, the multimode bosonic environment. And this can be useful, for example, in these two applications. So one is if you wanted to do some simulation of transport across these complex molecules, it was proposed here to do it if you could engineer some arbitrary Barth spectral functions to mimic the properties of this molecule. Another example is this simulator based on the atom photon bound states, where I will come back on that later, but here you need some photonic band, and if you can couple a quantum emitter and tune its frequency just outside of this band, you will now have this kind of dress state of this atom photon bound state, and depending on the detuning, you can control the size of the photonic cloud around this bound state. And now if you have several of these guys, you can just play with the detuning to control the interaction with this weird exponential shape, have some directional coupling and so on. But now again, we need to properly engineer this photonic band. And this is what I will be discussing in the first part of the talk. So I will be showing you how we develop this nice material of using a high kinetic inductance, and then how we use some topologies to actually quantify the disorder strength in these devices. Then in the second part, I will show some preliminary work that are still in progress, where we are starting to couple some quantum emitters to these metamaterials. Okay, so there are several ways that have been used in the community to engineer this multimode environment. An example here is this photonic crystal, where you basically step the impedance of, of a transmission line, used in the group of Andrew Hauck in Princeton. Then here it's similar idea where you actually load the transmission line with lumped element resonators. And another possibility is to use very long junction arrays that you heard of on Monday. Now, a final possibility is this concept of coupled cavity arrays, where we just have a bunch of LC resonators capacitively coupled together. And this will be my focus today. Very brief intuition on what we expect to see from this multimode environment. So I will start with just two bosonic modes, two harmonic oscillators. And if we just couple them together, and they have the same frequency, we can just measure the transmission of this tiny chain. And we just expect to have two peaks splitted by the amount of the coupling between these two modes. Now, if we have many modes all at the same frequency, we expect to have, well, n modes for n cavities, and the bandwidth will converge to 4J. Okay? And the way we implement this resonator is using this niobium nitride, very thin film disorder superconductors. So they have intrinsically very high kinetic inductance. And on the left here, you can see an example of just one LC resonator. So this part here is a meander to implement the inductor. And here we just have a capacitance to ground, which is shown in blue here. And yeah, these materials are nice for several reasons. Two of them, they have a high characteristic impedance, a few kilo ohms. And this will allow us to enhance the coupling to the charge qubits that we are using. And they are pretty compact, that I will show you in the next slide. Yeah, and this material was developed by Simone, a current member of the group. And yeah, we can have pretty reproducible and uniform films with pretty high quality factors. Now about the compactness. So this is the typical coplanar waveguide. So really a distributed transmission line that is yeah, from few millimeters to even centimeters. Now you can use a lumped element resonator, not distributed. But if you use a regular material, a non-disordered superconductor, the size will be typically of like 0.5 millimeter. And thanks to our high kinetic inductance, we can reduce this size even more to just like typically 40 micron. So this will allow us to pack a lot of this resonator on a small chip. Now, this concept of coupled cavity arrays, right? We have these LC resonators that we just capacitively couple. And as you will see, by playing with all of these L and Cs, we can engineer the shape of the band of the metamaterial. And so if we arrange them like that, this is typically what it will look like. Now, I told you that they are compact, but you need to have pretty good qualities to actually have a nice transmission, even with a lot of resonators. So this is a typical chip, which is a 4x7 millimeter. And for now, I will just make an array with all equal LC resonators. So all the frequencies are equal and all the hopping are equal. This is really a basic tight binding model, right? And if we now measure this chip in transmission, so we put an input signal on that side and measure the transport on the other side, this is typically what we get, which is similar to what I was showing in this introduction slide. And we can resolve most of the states. They look pretty ordered. And if I zoom in on the low frequency part, we have actually a pretty dense mode spectrum. And this is interesting for us because if now we can couple a quantum emitter to this region, the typical coupling we can achieve is much larger than the mode spacing. So we can enter in this multi-mode coupling regime that I will show later on. So we can put a lot of resonators. Now I want to show that we can also control the coupling over a pretty large range. So in this case, we were using a very small capacitor to couple all the sides together. And so the band is very narrow, but we can just increase the value of the capacitance to increase J and to reach more than 100 of magnitude for this parameter. Then now we can just play the game of having two different hoppings to have some intercell and outer cell hoppings like that. And this will create a band gap in the spectrum. So this is just a simulation. As a function of this ratio, you can control the value of this band gap. And we just fabricated some devices with two different ratios. And this is what we observe for the two devices. So yeah, we just control the size of the band gap, right? Then you may see it coming, but you can actually engineer the boundary conditions of this chain to have some topological SSH states. This is really the first step if you want to engineer the simplest topological chain. And yeah, you expect to have this localized mode on the edges, right? Yeah, so this is the first realization with this value of coupling ratios. So here I'm plotting a simulation of the expected decay of the SSH states. And this is what we measure in transmission for different devices with increasing number of sites. So if you have a very small chain, you can actually have some hybridization between the two edge states. And you can see them here in transmission in the middle of the band gap. And as the chain is getting bigger, they hybridize less and less and are harder to resolve. Now we can play with the hybridization also by playing with this coupling, which is what I showed just here. Now with a weaker ratio, they hybridize more. And this inter-band gap states are easier to resolve. Now, I want to show another way we have of measuring. So here, all the measurements were done in transmission, meaning that I was always putting my input signal on one side of the chain and looking at what's coming out the other way. But we can also do some reflection measurements, meaning that we pump one side and collect the signal on the same side. And these are the data here in the top and the bottom. So this is the magnitude, and on the bottom, the phase. And we see that for this device, even though the mode completely disappeared in transmission, they are still, the in-gap mode are still visible in reflection. And from the left side, we see just one mode, and on the right side, just the other mode. At a different frequency also. And this we actually attributed to disorder in the system. So now let me just briefly highlight the actual sensitivity of SSH states to disorder. So we are always talking about robust topological phase, but because this is a symmetry protected phase, right? If you have chiral symmetry, it's protected. And you can see here that these two states there, I mean, if you just have some sigma X and sigma Z term, the only way to connect these two is to close the gap and to actually have a transition. But as you know, if you have any sigma Z term, you now have a trivial way to connect the two, and you lose the protection. And in our case, the sigma Z is the on-site frequency disorder. And if you think in terms of the initial parameters, the L and C parameters, any variation in inductance or capacitance will break the chiral symmetry. So what you see is that this topological phase is actually very not robust and very sensitive to disorder. And then our idea was to actually use this sensitivity to disorder to find an easy way to quantify the disorder strength in our devices. So when you have many modes, it's actually quite hard to estimate the disorder because you have many degrees of freedom. And here we will reduce it to just look at the SSH states. And yeah, we like to coin this guy the topological disorder meter. So yeah, I come back briefly to the hybridization between the SSH modes for small chains. Here it's only 14 resonators, and you have a finite overlap between the H states. So these modes here, they will have a splitting, and this splitting actually depends on the hybridization. And if I increase the size of the chain, I will reduce the hybridization and thus also reduce the splitting. And so what I will be looking at now is for many different realizations, many devices, I will just plot the value of this SSH mode splitting that we call delta topo. So this is what I'm reporting here. And you see that the general trend is here, meaning that if I increase the number of resonators in the array, this splitting is going down, but it's not converging to zero. And this is really because of disorder. So now this is just the simulation of the zero disorder case. If now I do some random simulation with non-zero disorder, this is the typical curve I get in red. And by properly fitting the data point to such disorder case, we can extract it, which I explained just now. So the analysis goes this way. So for each fabrication batch and number of resonators, we generate some probability density function. So we can take, for example, this plot here. So for one value of disorder, at zero disorder, we get an histogram on the y-axis, and you get just one bin, which is what you expect without disorder. Now, if you increase disorder, the expected value for the mode splitting will just increase. And we repeat that for different number of resonators. We generate all this PDF. And now we actually compute the disorder likelihood from the experimental data we measured. Meaning that for one experimental measurement of the gap splitting, we look at the likelihood for each value of disorder to get these curves here. So each square is for a different fabrication batch. So we get different values of disorder, but we can just extract the maximum likelihood for each curve, which would be these points here, and just take the combined likelihood to get a typical estimate of the disorder, which would be on the order of 0.2%, which is quite small and actually comparable to these much bigger resonators. So this analysis would have been quite hard without using these SSH states. We would have had to fit the whole 64 modes and so on. Yeah, and now let me just conclude this first part. So we showed that basically we can control all the parameters of this platform for multi-mode environment. We have a large mode density and high impedance, so it should be nice for strong coupling. And on the way, we use the topology to have a neat way to estimate the disorder that is actually quite low in the platform. We also had some fun doing some other lattices that I don't have time to go into, but some left-handed metamaterials, for example. We started to do some 2D arrays or some flat band lattices. And now what's actually missing in this platform that we don't have for now would be one to have actually a strong non-linearity in the bosonic environment. That would be very nice if we wanted to study interaction or correlated phases. But for now, we are still not there yet. The non-linearity of these guys is very small. We don't have a neat way to break time reversal symmetry or to engineer non-reciprocity for topology. I mean, we cannot, for now, engineer arbitrary spectral densities. But this could be done maybe with some inverse design technique that we are starting to look into. Okay, now for the second part, we will take these bosonic modes and just couple some quantum emitters. So this is a chip. Here you see all these wire bonds, and this one is actually a 2-qubit device, but I will start with a single one. And I come back briefly for the motivation on this idea of atom photon bound states. So we showed that we can create such a photonic band here. And now if we have a quantum emitter and we can tune its frequency, we will be able to control the photonic cloud around it and control the interaction between two atom photon bound states. And what I didn't mention before is that these bound states, they can inherit the properties of the photonic band. Meaning that if you have some non-trivial band, like the SSH one, it was shown in this paper here, that the atom photon bound state will inherit some of this property, and you can use it, for example, to engineer directional coupling between qubits, which can be quite interesting for simulation purposes. And if I look at the state of the art of this field, it advanced pretty quickly from just 1 qubit to 2 qubits, 10 qubits in this paper here. But the common point of all these architectures is that the emitter is always coupled to one side of the lattice. As you can see here, this would be 1 qubit, or here this would be 1 qubit. And our idea to test the platform was to just have a qubit of the emitter to many points of the lattice to see what would be different from what was observed before. So this is the actual device, how it would look like. So in green here and white, it's the same LC resonator as I showed before. And now in red, that would be the body of the qubit, which is a transmon qubit. And you see that it's coupled to basically 5 sides of the array. On the bottom, you have all the control lines. And I don't have a full-scale picture of the metamaterial, but it has 44 sides. And it is actually in the SSH regime, as I showed before. But for the measurement I will show later, we for now don't use this SSH state. And yeah, the qubit is really in the center of the array. So I will quickly describe the different control and measurement possibilities we have. So as before, we can do some transport measurement directly on the metamaterial. So you can measure transmission or reflection directly on the bosonic sites. But we can also address the qubit. So we can tune its frequency, apply some gates, and read out its state. So now with this toolbox, I will start with the first measurement, which is just a spectroscopy or measurement of the metamaterial modes with the qubit tuned far away. So this should look just like what I showed before. And this is the transmission we get with, again, the 2 bands, a band gap, and some state in the middle. And we can resolve all the modes, meaning that we have a pretty low disorder. Then the next step is to tune the frequency of the qubit across all of these modes. Now you expect to see some avoided crossings. And this is the resulting map. So here, one vertical line cut is what I just showed before. And on this axis, we are tuning the frequency of the qubit, see across the band, up and down. And if I show just to zoom in on 2 parts, we see that the coupling profile is not uniform. It's relatively complex. So here in the bottom, you can see that some coupling are very weak, like this one, and some are stronger. And you have kind of this on and off behavior that I will explain in a second. And these 2 zoom in have different scale, but it seems that the coupling is increasing in this upper band. And these 2 effects, we can understand it pretty simply. So now I'm just showing again the eigenmodes of the system. And if we look at the spatial localization, we just have your usual harmonic standing waves. And the qubit is coupled in the middle. So for the top modes here, we will have a very large coupling, whereas this one is antisymmetric around the qubit position. So you expect a 0 coupling. And for the lower band, the modes are oscillating very fast. So the coupling will basically average out to 0 or to small values in the lower band. All right. Now, here I was just tuning the qubit across the metamaterial, but always measuring the metamaterial, not the qubit itself. Now we can do a two-tone spectroscopy and measure directly the qubit state. So this is the actual measurement sequence. So very briefly, we change the frequency of the qubit with this blue pulse. Then we apply a pi pulse to excite it, and we bring it back to a nice point for readout, and read out its state via this extra resonator. And these are the extracted data points. So in red, it is the end of the upper band. And what we see here is actually the atom photobound state, so the qubit above the metamaterial. And I can combine these two types of data in this plot here, where you see both the atom photobound state and the metamaterial. Now we can take this data and perform a global fit, fitting to this model, just in the single excitation spectrum. And this is the resulting fit. So yeah, I'm showing the result of the fit with this orange dashed line. And you can see, for example, in this zoom in, the fit corresponds very well to the data. Then the bare qubit that we extract from the fit is actually this blue line. And you see that it's going relatively far away. I mean, the crossings here in the band are happening far from the bare qubit, not around the bare qubit. And this is a peculiar feature that is actually due to the strange coupling profile, so I don't really have time to go into that. But now let me show you, this is the extracted coupling we get. So this is really the coupling of the qubit to each physical site of the lattice. And we see that this coupling is important for basically 5 sites and then decay to 0. Now we can diagonalize this initial mode to get the eigenmode of the metamaterial, and we can also get from the fit the coupling of the qubit to each of these modes. And this is basically the amplitude of the avoided crossing I was showing before. And you can see the on and off behavior, that for the lower band it's very weak, and for the upper band it's really increasing and shooting on the edge. Now I can plot another metric on the same graph, which would be the sort of density of state, which in this case is just 1 over the frequency splitting between 2 modes. And you can see 2 effects. If we focus on the upper band, on the edge, the modes are getting condensed or closer in frequency. So the density of state is actually increasing. And at the same time, the coupling is increasing. And now I can use another metric, which is basically the ratio of the two. So this would be the ratio of the coupling divided by the frequency splitting. And this, we want to use it as sort of a multi-mode coupling indicator. Because if your coupling is much larger than the splitting, right, you will be coupled to many modes. And in this lower band, this parameter is smaller than 1. So we have sort of single mode coupling, whereas here, it's really shooting on the edge and reaching values of order 10. And now we'll see the effect of this coupling, this multi-mode coupling. So for that, I will go back 1 step and consider a very simple toy model, at least in this linear limit, which is a quantum emitter coupled to some equidistant modes with a constant coupling to all the modes. And for a very weak coupling, you get these tiny avoided crossings. And now I will just ramp up the coupling. And in this animation, this is what we get. So the crossings are increasing. And when we enter this multi-mode regime, the coupling are becoming very shallow. And at the end, you don't see any crossings anymore. Right? So I can run that once more. Yeah. And so for this transition, we actually can look at another interesting parameter, which is the participation of the qubit in each eigenmode. So imagine that you just have a qubit coupled to 1 mode. If they are on resonance, the participation of the qubit will be 50% in each mode, right? They are fully hybridized. And this is what we see in this case here. So yeah, now for each of this eigenmode, you see that the qubit goes from fully in this mode to fully in the orange mode, fully in the green mode, and so on. And at the crossing, it's 50%. So this is actually a log scale. And now I again increase the value of the coupling. And you see that the participation of the qubit in each crossing is getting weaker. And if I keep increasing the coupling, this participation becomes very weak. And in this extreme case, deep in the multimode regime, the qubit is actually almost not participating in this weird actually not avoided crossing, but in this weird transition. Like the qubit is always in these two states there on the bottom and on the top. Okay, so now I will repeat the same analysis for our device parameters. So here on the left, I'm showing again all the crossings we measured. And on the right, I'm showing the participation of the qubit in each of these crossings. So in the lower band, you see that the participation is close to like 40%. So it's nearly a single mode coupling. And if we go in this upper band here, this participation is really going down to very small values. And so within a single device, we have this transition. And yeah, I will now finish with that. So if I focus on a single crossing, on the right, I'm showing the participation of the qubit. And on the middle, I'm looking at the population of the state really in real space in the lattice. So at first, here we included some disorder, but the mode is scattered all around the chain. And if now I sweep across, you will see that on resonance, the qubit site, which is this red part here, will dominate like to 50%, and the state is delocalized everywhere else. So I just go to the resonance case here. So you see that the qubit is participating to 50%. The actual sum of all of these states would be 50%, but it's spread all around. Now I repeat the same in the multimode coupling regime that we have on the top of the upper band. And this is what we observe. Simulate. You will see that now the qubit is never participating more than 5 or 10%. And we see that the modes actually localize on resonance on the left and the right side. So now if I focus again on the resonance, you see that one of the modes is really localized on the left of the array, and this one is localized on the right of the array. And actually this we can observe from the experiment. So now I'll show you a measurement on this exact crossing. And in this case, we are not measuring the transmission of the chain, but the reflection on the left and the reflection on the right. And you see that if you measure from the left, one mode is disappearing. And if you measure on the right, the other mode is disappearing. And this is because on resonance, these two modes are really localizing. And this we now interpret it as the qubit acting as kind of a mirror or a domain wall in the middle of the chain. And if you probe in reflection, you will only see one of these two modes. And so now we can really control this localization, and maybe this could be used as a sort of way to engineer some directionality, playing with the detuning. Right? If you had several qubits on the chain, for example. And just, yeah, so if we do the same measurement for a small crossing, these two lines, they remain from the left and the right side measurements. So we don't see this effect in reflection. And yeah, as a last teaser, we can do some time evolution, some time domain measurement of the qubit, but this is really ongoing work. And we see this kind of Rabi oscillation, and we want to understand how it will work in this multimode regime. And yeah, just finishing, I want to say that in the beginning, I was mentioning that we worked on the bath engineering, really the engineering of the density of states, but we could also work on the engineering of the coupling profile of the qubit to all the sites and control where it's diverging or not. And yeah, we have some device with, for example, 2 qubits that are also on the way that we are starting to measure. Thank you for that.
Very nice overview. Maybe just a quick technical question. So you discussed that you are at the moment you're still limited by the degree of homogeneity that you can reach. Mm-hmm. So what is the technical challenge now? What can you push this number?
Yeah.
Your
mm-hmm. So I did put some value for the current platform, the nonlinearity we have. It's just here. Yes, this is the nonlinearity that was extracted in this paper. And you see that it's in the order of 10 Hertz. And our typical coupling is in megahertz, the frequency in gigahertz. So this is really super weak. Now, the way to have high nonlinearity is actually with the first thing I mentioned, with junction arrays. With this kind of devices, you can have much bigger nonlinearities, megahertz, but then the disorder is also much bigger. So it's quite tricky to engineer long chains. And this could be scaled to few unit cells, but for sure not 100. And this is actually a very interesting direction to try to scale this platform to several sites. And we have some work going on some arrays of this K-resonator towards Bose-Hubbard, the strong interaction limit. But for now, it was quite disordered.
Yeah. Well, mentioning that you also have access to reading the dynamics, like a super dynamic, and also like a recovery dynamic that you understand kind of
So at the end, I showed some time domain measurement where we were looking basically at the decay of the qubit. And if the qubit is pushed in the band, it will couple with nodes, and we see Rabi oscillation between the qubit and some nodes of the array. But we were also looking at if the qubit is just above or below the band, how is the decay looking? And maybe this decay will look relatively weird. So if you were really in a non-Markovian regime, you could see some revival effects on your things, and we are looking into that.
Okay, then you've done this, then let's figure again if you want to that one.